Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus 1, the first lecture, Lecture 1A, Sets and Functions. If you are in my class, there's a set of notes posted on Canvas. Feel free to go to those notes. If you are not in my class, there's a link in the description below, or if you are in my class, you can get them there. There's a link to in the description below, and it will take you to a set of notes online. And as you can see, those notes here are slightly different than the ones that I'll be presenting in class. So you can have a few different examples, and the definitions are the same, but some of the examples are slightly different. So you can have a slightly different perspective on this material. Okay, so what we're going to do is we're going to start by talking about the definition of a set, some examples and some special sets. In the book, this is sections 1.1 and 1.2. We'll talk about ordered pairs. We'll talk about functions, ways of doing different types of things, and then we'll ways of representing functions. And then what we'll talk about is sequences, which are a special type of function. Now, our approach here today is going to be slightly different than the one in the book. The book is a very good approach, but it's very intuitive. Now, later on, when we're dealing with derivatives, we're actually going to find that these derivatives are functions of functions. They take a set of functions and they transform them into a different function. So they take a function as an input and give a function as an output. The derivative is one of these. It's called an operator that does this. Now, if you understand functions in this intuitive approach as the book does it, with only functions of numbers, you miss something. That functions can be more. If you have this, so what we're going to do is we're going to have a more formal approach here in the lecture and in our first problem set, which you'll do the first week. We will have a very formal perspective, and what we're going to do is talk about functions only as sets. And we're going to start mostly with discrete functions. We'll do a couple of infinite ones, but really what we want to focus on are finite functions in order to get this idea that functions are just sets, and that I can have functions of functions. That's just a set of a set. So what we want to do is we want to have this perspective so that later on we can use it to understand the derivative a little bit better. Okay? So here it is. And this is the big point where I'm going to differ from the book. There's going to be a couple more. They come at the very beginning and the very end of the class. So you'll see that kind of the sets and sequences, I'm going to set that up slightly different, very differently than the book does. Then we kind of jam right into doing things the way the book does. And we'll follow that along for Module 1, Module 2, Module 3. And then in Module 4, at the very end, we're also going to deviate from the book. So just heads up about that. Okay, enough said about that. So, a set here, we're going to define a set as any collection of elements where each element is distinguishable. The order of the elements does not matter, and there's some technical stuff that we really don't need to worry about. Stuff like a set cannot be a member of itself, so I can't have like a set of all sets because then the set would be a member of the set of all sets. And other technical things. If you're interested in those technical things, I recommend a discrete class or a class in logic. That will include those technical things. We don't really care. For us, it's just enough to know that every element is distinguishable and the order of the elements does not matter. So what do I mean by every element is distinguishable? So if I take a deck of cards, right, and I just hold up a deck of cards, these are Margaritaville cards, in case you want to know. I've got the 8 of hearts, and that is distinguishable from the 2 of hearts. So in my 52 card deck, right, the 2 of hearts is different than the 2 of diamonds. So in my 52 card deck, each card, I could tell the cards apart, right? There's no duplicates. All right. Now, depending on your deck, the jokers might be duplicates. So if I include the jokers and they're exactly the same, if I've got 2 jokers that look exactly the same and I have them in the deck, I can't distinguish those elements. That's not a set. I have to be able to distinguish the element. Now, I could distinguish it by writing a little 1 on one of them, and then I know which one's which.
Me?
So that's the idea of a set. Here's 52 cards, all of them distinguishable. Furthermore, the order doesn't matter. It doesn't matter if I have the 8 of hearts here or if it's the 2 of hearts and I shove the 8 of hearts in the back. It's still a set. It's still the same set. Okay? The order of the set does not matter. It's like a hand of poker, right? If I have the ace of spades, the jack of spades, the ace of hearts, the 4 of clubs, and the 10 of clubs, I've got a pair of aces. It doesn't matter if they're in this order, right, or this order, or this order. It's still a pair of aces. All right. So that's the idea behind that. Let's give some examples, other examples. So a deck of cards is a perfect good example of a set. Every item's distinguishable, and the order I put the items doesn't matter. Okay, other examples is A equals 1, 2. These are the elements. This is A, it's got 1 and it's got 2 in it. Here's B, it's got an A and a B in it. Now, the way I say that something is an element of a set is I use this type of thing here. I use this kind of weird-looking A. I'm sorry, weird-looking E. So I've got 1 is an element of A. 2 is an element of A. Here's another set. C, it's got 2 cats in it, McCavity and Gus. I've got 2 dogs in D, Rover and Jack. And E is interesting. E is the set holding the sets A and B. Okay? Now, 1 is not, and here's how we write not, an element of E. The set 1, 2 is an element of E. All right, so that's not exactly what you expect, okay? I've got the set of sets here has 2 elements in it, the set A and the set B. It doesn't have 4 elements in it, okay? It's a bag, and inside are 2 bags. There's 2 things in each of those things on the inside, but I don't count those. I only count the 2 bags that are in my big bag. All right? Okay. Let's go through some special sets. The empty set is just a set with nothing in it. Notice that I use these little curly brackets to denote that. Okay. The natural numbers, 0, 1, 2, 3, blah, 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 42, 43, 44, blah, 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 6,786, blah, blah, blah. Those are the natural numbers. Some books have 0 included. Some books don't. It actually doesn't matter from a math point of view. You just change the formulas in your sequences. Oh, you started 1. Okay, well then we subtract 1. Oh, you started at 0 instead of 1. Oh, we just add 1 to the formula. I mean, they're logically, they're absolutely equivalent. You just have to fiddle with the definitions a little bit. The integers, and just check. Is 0 included in this list or not? Check in your whatever book you're using in the future. Just make sure. This integer, with the big Z, denoted by the big Z here, these are the integers. So these are all the positive numbers, the natural numbers, and then we throw in the negative numbers. All right? And the big thing about the negative numbers is that they add with the positive counterpart to 0. So I take 1, and then I say, let's create a number so that 1 plus that number equals 0. We'll call it -1. So we've right? God gives you these. These are, you get naturally, the natural numbers. These we've invented, right? You want the additive inverses. Here we're going to add in the multiplicative inverses. We're going to add in the fractions. This right here is the rational numbers. This is called set builder notation. Let me show you how that works. Okay. This rational thing, Q here, it's P over Q so that P is an integer and Q is a positive integer. All right. It's any number that can be expressed in terms of a integer and a positive integer, the ratio of those two. So, for example, 0 is a rational number because it can be represented as 0 over 2. 1/2 is a rational number. It's 1 over 2 or 2 over 4. There are multiple representations. 2 is 2 over 1. It's also 4 over 2. All of those are representations, rational representations of this number 2. Okay. Negative 1/4, integer on top, positive integer on the bottom. 1 over negative 4 would also work because the negative can just be moved to the top. Okay? Pi is not a rational number. And neither, we won't prove this, but that's just, hello, pi is not a rational number. The square root of 2 is actually not rational, and we're actually going to prove this in this class. So during Module 3, we're going to prove that this number is not rational. There's no way to represent it as p over q with p as a integer and q as a positive integer. It's kind of a cool proof. And we've got 2 more sets here. The real numbers, which is what we're going to be concerned about largely in this class, R is the way we represent it. We're going to define that next time. And then we've got the complex numbers, x plus yi, where x and y are both real numbers. This, by the way, this real bit is just a marketing ploy. There's nothing real about the real numbers, right? The only numbers that God gives you are these natural numbers, and everything else we're just tossing in other stuff that we want. Okay. All right, so those are some common sets. Can you think of, let me ask you a question then. Pause the video and answer it for yourself. Are the following rational? All right, so let's add, what about pi over 2? Is that rational? What about 16? What about e? What about the square root of 16? And what about the square root of 3? What do you think? Do you think these numbers are rational or not? So that's just a little question to think about. Go ahead, pause the video, think about it, unpause it when you're done. Okay, so now let's talk about ordered pairs. All right. And it should be noted that we're talking about ordered pairs, but we can generalize this to order triples and order quadruples and intuples for any natural number, right? We can have 16 tuples where there's 16 things and the order matters. And we can have, in fact, we can have infinite lists where the order matters. But what we want is a pair of elements from some set where order matters and repeats are allowed. Okay? So here's an example, 0, 1, both natural numbers. McCavity Jack, this was one of the elements of C above. When I defined this like McCavity Gus and D was Rover Jack. I've got an ordered pair taking one element from here and one element from here. That's legal. McCavity Jack. The order matters. That's important. So 0, 1 does not equal 1, 0. And duplicates matter. So I can have, and duplicates are allowed. So I can have the ordered pair 1, 1. Okay. By the way, there's a little note here. The book denotes ordered pairs with parentheses. A more modern thing to do is to use angle brackets. Both are legal. The reason why I've moved to angle brackets is because it makes this less confusing. So when I write on the board the angle bracket 1, 2, that means I want the point x equals 1 and y equals 2. If I write parentheses, what I want is the set of all real numbers strictly between 1 and 2. So this is, a bit of a line. This is a point. So just a heads up, that's what I'm doing there. You can use whatever you want to in this class. If you prefer the parentheses, as long as someone understands what you mean, that's fine. As I said, I prefer using the angle brackets just because we're not using the angle brackets yet. And it can distinguish between points and parentheses, points and intervals. Okay. So let's look at something bigger called the cross product. So here's a definition. Let A and B be sets. So now I want A cross B, and this is read A cross B, by the way, is the set. This is set builder notation again. of points x, y, so that x is in A and y is in B. Right? It's a set of all possible ordered pairs where the first element comes from the first set and the second element comes from the second set. So, for example, if C equals 0, 1 and D equals AB, then C cross D would equal 0. Right? I picked up the 0 here. 0, A. Then I would do 0, B. Then I would do 1A, and then I would do 1B. And it's just a set of ordered pairs. Okay? And if we've got a set of ordered pairs, we usually call the elements and the points. Okay? Just to distinguish them for just elements. You can use elements too, but people tend to say points because it's immediate that this is a thing on the graph. All right. So what other sets of points can we have? Oh, just a question. Why is A0 not in C cross D? Just as a thought. All right, so we have this idea of points. Let's go off to the big thing, which was to formally define what a function is. And here's the intuition, okay? The intuition is I have my deck of cards, okay? Without the jokers. I've got 52 cards. Now, what I'm going to do is I'm going to make piles of these cards. I'm going to have, say, 4 piles, all right? What I'm going to do is I'm going to take couple of these cards, and I'm going to stick them in this pile. A couple more cards, and I'm going to stick it in this pile. And I want to get rid of all the cards. So I've got my 4 piles of cards going. Some here, some there. And in the end, I don't have any cards left in my hand, right? I've got 4 piles of cards, and I have no cards left in my hand. Now, if I'm doing this with cards, can I put the 7 of spades in more than one pile? And the answer is no. If it goes in the first pile, the 7 of spades is done. Okay? So for every card has to go in a pile, and every card can go in only one pile. It can't go in 2. Right? The cards cannot be beside themselves in 2 places at once. So that's the idea here. That's the intuition. I'm going to put every card in a pile, or associate every card with a pile, and I'm only going to associate it with one and only one pile. No, I can't put a card in 2 piles at the same time. So, f is a function from x to y if for every x in x, there exists a y in y, so that the point xy is in f, and if x1 and y1 and x2, y2 are distinct points in f, then x1 cannot equal x2. So for any 2 points in f, if they're different, the x values don't equal each other.
I think I speak for everyone here when I say, huh?
There's an easier way to say this. This first condition simply says every x gets used. The second condition says no x is used more than once. That's all those 2. That's a very complicated way of saying every x gets used and no x is used more than once. Let's consider an example. All right? Let's let our big X be 0, 1 and our big Y to be 0, 1, 2. Now, is F the set of ordered pairs 0, 1 and 1, 1 a function? Answer is yes. Why? I used every X, right? I used 0 and I used 1. I didn't use any X more than once. That's the first one. That's the second one. I've got them both, but I don't have any repeats. Contrast that with this thing here. G is not a function. Right? Nor is H. Here, I didn't use 1 as one of my x values. I was missing that one. There it is. And here, I use 0 twice. Now, it is legal to use y twice. That's fine, as I did here. These are not functions. This is, yes, a function. These are not functions. Okay? All right. So let's put some definitions down in here on the pieces of a function. If f is a function from x to y, we write this f colon x arrow y thing to say f is a function that takes x values and makes them y values. Or f takes from x and goes to y, or f comes from x and goes to y. X is called the domain. This big X here is called the domain. This big Y here is called the target, codomain of f. And this set right here, so neither of these are the ranges. Don't confuse the target with the range. The range is something different. The range is the Y's I actually hit. The target is the Y's that would be valid. The range is the ones I actually hit. So let's look up here. Here in my example, the domain is x. Which was 0 and 1. And my target was y. And the image or range of this function would be the y values that I actually hit. So I hit 1 with this x value, and I hit 1 with that x value. So I don't hit 0 and I don't hit 2. They're valid outputs, but I don't actually hit them. So the range of this would simply be the singleton, or the element 1. Well, it would be the singleton 1. The set containing only 1. Just a caveat. This arrow is going to mean a lot of different things in calculus. It's I want to say it's like a homonym in English, right? Math is a language. The arrow is overused. We're going to say that in this context, this arrow here means that, so just some examples of what we're going to have. Later on, we're going to have x goes to a, which is going to say x is heading to a. We're going to have x goes to a from the left. We're going to have y goes to d from the right, or y goes to infinity. Okay, these are limit arrow concepts, okay? And they are different than this one. This one here is f takes values from x and transforms them into y. That's a very different concept than x heads to a in the x space. So just heads up that the arrow is going to be used several times in this class, and it's going to have different meanings depending on the context and what we're talking about. Okay. All right. So how can I write f? This right here is set notation. So let's write this again. F equals 0, 1, 1, 1. This right here is called set notation. Now, I can also write it in rule notation. So how would I write this in rule notation? I would say the following. This is the function 1, right? I've got 0, 1, and 1, 1. I could write it like this as a piecewise function. 0 if x equals, 1 if x equals 0, or 1 if x equals 1. But this right here is just the function 1. For any x, no matter what I put in, I get 1 back. So this right here is called rule notation. And it's the one you're familiar with. By the way, what is f of 1/2 here? Hit pause and answer for yourself. F of 1 here, f of 1/2 does not equal 1. f of 1/2 is not defined because x is 0, 1. The domain is 0, 1. Okay, so this rule notation here, set notation, I just list the elements. This is rule notation. Okay. Now, I can also do some visualizations here. All right, so this right here is called an arrow diagram. And here what I'm going to do is I'm just going to visualize where each one goes. So 0 here maps to 1. So from the x space, I go to the y space. Again, the arrow is being used in a different meaning. And here, 1 maps to 1 in the y space. And this is called an arrow diagram. I could also do a graph. Okay. And here what I'm going to do is I'm just going to draft the function. The functions is the points 0, 1 and 1, 1. Okay? And these are two ways of visualizing them. A lot of times you want to use different visualization tools. So when we talk about limits, we're going to use arrow diagrams a lot to do these things because they make a little bit more sense. They illustrate what we're doing with the limit a little bit better. But, you know, graphs work fine too. Now, why didn't I fill in anything here? So why don't I have a line here? Pause and answer. I don't have a line here because 1/2 is not in the domain. Okay. All right, so I don't want to connect these two with a line because then it would say 1/2 is in the domain. That's not true. The only things in the domain are 0 and 1. Okay. Let's look at another function. This one's going to be very important for us in this class. Matter of fact, if you don't know the visualization for this function, what I want you to do is go on Desmos. I'll show you how to do that in a moment. I want you to print out this function. I want you to put it above your bed, right there above your bed. So every night when you go to sleep, at night, you should see 1 over x. Okay? This is what you should see every night. When you go to bed, I want this to be in your brain, if it's not already there. Okay? You should see 1 over x in your life. All right? You're going to want this function. You're going to love this function. It's going to be one of the things that really helps you understand calculus. Okay? So let's look at this function. F. So we're just going to do the positive side first. You can do the negative side as well. But for the moment, we're just going to say let x equal 0, infinity. It's an interval. And we're going to let y equal all of r. So positive infinity, negative infinity. Okay. Let f from x to y be the function so let f from x to y be the function so that for all x, f of x equals 1 over x. Okay? This is the big example that we want to deal with. Now, here's the question. What's the domain of x? What's the domain of f? What is it? It's 0 to infinity. Why? Because I said so. What's the target? R. Why? Because I said so. What's the range here? The range is a little different. I'm only going to hit the positive numbers. So the range here is 0 infinity. If Now it's happenstance that the range and the domain are the same thing. They shouldn't. Normally they won't be. But if I only take positive numbers, I'm only going to hit positive numbers. Okay. Now, this right here is in rule notation. What would this be in set notation, by the way? In set notation, it would look like this. F would equal the set of ordered pairs, x 1 over x, such that x is in 0, infinity. Okay, if you want the set notation, you have to use set builder notation because these are infinite items. Okay. Now, let's do an arrow diagram for this function. Okay, so I've taken the x space and the y space. Note that the x space ends at 0 here. And the y space is all of r, even though we're only going to use the points from here over. The y space is still all of r. The target, that's fair. Now, what is f of 1? What is f of 2? What is f of 3? Now, as x gets bigger and bigger and bigger, what happens to these arrows? Right? They're just going to keep going this way and this way and this way. They're going to get closer and closer to 0, but never pass it. Okay. Let's look at what happens the other way. What is f of 1/2? So something very interesting is happening with this function. It takes big numbers and makes them really small. It takes small numbers and makes them really big. Along the axis here, kind of the axis of 1 mapping to 1. Okay? So if I'm smaller to 1, it's going to shoot me to something bigger than 1. If I'm bigger than 1, it's going to shoot me to something smaller than 1. And as I get bigger and bigger and bigger in the x space, I'm going to get smaller and smaller in the y space, or closer and closer to 0. Whereas as I move closer and closer to 0 in the x space, I'm going to move farther and farther and farther away from 0 in a positive direction in the y space. Right? This thing's going to shoot off to infinity. Now, a graph of that function, if we're only interested in the positive axis, is going to look something like this. And you can see that behavior happening here. As I get closer and closer to 0 in the x space, I'm shooting off to infinity in the y space. And as I get closer and closer to, as I get larger and larger in the x space, as I move over to the right in the x space, the y space, I get closer and closer to 0 in the y space. Okay? So this is the function 1 over x. And you should be, again, this function is your friend. You should have it for you. You should definitely know this function. You're going to want this function in your library because it's got some interesting properties. Okay. So now we've looked at a couple of examples. As I said, there are more in the notes online. Let's look at the last thing, which is sequences. So here's a definition. A sequence is a function whose domain is the natural numbers. Wow, that's difficult, right? Wait a minute. Any function whose domain is the natural numbers. So what do we mean by this? Well, and we have special way of writing it, right? So if I write the sequence Sn equals 1 plus n, right? This is the sequence. This is the function. Right? Here's what this function actually is. It's 0, and I'm going to map 0 to 1. 1 is going to map to 2. 2 is going to map to 3. 3 is going to map to 4. And so on and so on and so forth. Right? It's a function. The natural numbers is its domain. Okay? What about Tn here equaling 1 over 1 plus n? So this function, 1 over 1 plus n is my rule. So I'm going to map 0 to 1 over 1. 1 is going to map to 1 over 1 plus 1. Here I'm going to have 2, which is going to map to 1 over 3. 3 is going to map to 1 over 4. And so on and so on and so forth. It's just a sequence. Now, because this is just a sequence, I can also write this with special notation. I can just write the elements of the target, the y values actually hit. I can just write them as an ordered tuple, and it's an infinite ordered tuple. Okay, so just like we had an ordered pair, I just write the y values here as a tuple: 1, 1/2, 1/3, 1/4, and so on and so on and so forth. And I just write the y values. So sequences have some special notations, but they're really just functions, where the domain is a natural number. And there's one more that's very important: a rational sequence. A rational sequence is a function s, I'll just use s, from the natural numbers to the rational numbers. Okay, so a rational sequence is a sequence whose target is Q. All right. Okay, so what have we talked about today? We've talked about a couple things. Let's just recap very quickly. We have sort of definition of a set. We went over a couple of these sets. Note here these rational numbers. These things are going to be important for us later on. We're going to see them a little bit. They're going to be important for us next time. And then they're going to be important when we start talking about rational functions, what they are. And then they're going to be a little bit more important as we go on in the class, especially in Module 3, where we actually prove some of the things about this. Okay? We give notations for the real numbers and the complex numbers. And then we did some examples, and we did examples of ordered pairs, and we defined the cross product. And then we defined a function, and that was the big thing. A function from x to y is a set of ordered pairs. Okay, it's a set of points where every x gets used and no x is used more than once. And we did a couple of examples. And then we did these visualizations. We've got arrow diagrams and we've got graphs. And again, we did the arrow diagram for this one. And then we did the graph on the computer. And then we defined what a sequence is, and we're going to pick up there next time. Okay? If you have any questions, you may ask them. Please do on, you can send me an email, or even better yet, ask them on Discord. And don't forget that there is a quiz on Tuesday and another one on Thursday again. That's it for me. Thank you very much, and have a good one.
Now, don't forget